Hi everyone, we are Team 9 and my name is Haechan Kim. From now on, I'm presenting about the paper titled On the Trade-off Between Robustness and Fairness. This is a brief summary of this research. It found theoretical experimental the fact that adversarial training easily leads to a more serious robust fairness issue and proposed a fairly adversarial training which called FAT method to address this issue. First, I'll explain on adversarial training, which is the background of this paper. In 2019, the paper titled Towards Deep Learning Model Resistant to Adversarial Attacks points out that deep learning models are vulnerable to adversarial attacks. Also, this research proposed the adversarial training technique to overcome this issue. The first figure illustrates how traditional machine learning training is vulnerable to adversarial attacks. Considering an image classification task, we can create a perturbed image by adding noise to the input image that is imperceptible to humans. Since the model trained on the original data has not been trained to recognize these perturbed images, it may misclassify them. Adversarial training involves adding perturbation to original training data during the training phase, helping the model adapt to these perturbations. The illustration below shows adversarial training as described in the paper. A simple decision boundary formed using only the original training dataset may lead to misclassification when infinity norm perturbations are applied, which is depicted as stars. Thus, through adversarial training, the model achieves a more complex decision boundary capable of withstanding adversarial attack. Recently, numerous papers have identified an interesting robust fairness phenomenon in adversarial training, specifically that a robust model well trained by adversarial training exhibits a remarkable disparity of standard accuracy and robust accuracy among different classes compared with natural training. Usually, the performance of natural trained model is similar across classes. However, adversarially trained models tend to perform well in some classes and poorly in others, which will lay serious hidden dangers in some applications level. Experimental results of the original paper in Figure 1 and Figure 2 suggest that there is a trade-off between average robustness and robust fairness. With the increasing perturbation radius, adversarial training is able to improve the average robust accuracy of models over classes, but it also leads to a large variance of class-wise robust accuracy. Their core contributions can be summarized as these three. The first one is they empirically find the relation between the variance of class-wise robust accuracy and perturbation radius in adversarial training. Namely that adversarial training with larger perturbation radius will lead to larger variance of class-wise robust accuracy while average robust accuracy is improved, which suggests that there exists a trade-off between robustness and fairness. Second, they theoretically analyze this new phenomenon above and provide a potential explanation for it through a linear model with mixed Gaussian distribution. Additionally, they theoretically proved that adversarial training can lead to severe robust fairness issue compared with natural training. The last one is they proposed FAT, which stands for Fairly Adversarial Training, to mitigate the trade-off between robustness and fairness, and experimental results validate the effectiveness of their proposed method. This is the detail of experiment setting. You can see that they choose the average robust accuracy and variance of class-wise robust accuracy as evaluation metrics for robustness and fairness respectively. Also, the experiment conducted to observe the changes in robustness and fairness by perturbation. In Table 1 and 2 show that as the perturbation increases, the average robust accuracy also increases, but the variance of class-wise robust accuracy also increased. This means that as perturbation increases, robustness improves, but fairness decreases. To describe multiple classes which consist of several Gaussian distributions for each class, they use mixture Gaussian distribution. Additionally, to simplify the problem, they designed two classes plus one class and minus one class, and then they analyzed the performance of natural training and adversarial training on each class. You can check the annotations on the box, and the mixture Gaussian distribution is defined as here. Two classes plus one class and minus one class are on each Gaussian distribution, and the prior probability of class is based on alpha. From now on, we focus on studying the performance of linear model on distribution D star as described here. The theorem 5.2 states that for the naturally trained linear classifier FNAT that minimizes the natural risk. And there's the cumulative distribution function CDF of standard Gaussian net distribution, and the k is positive constant. So the cumulative distribution function is monotonous increasing function. The theorem 5.2 shows that if the variance of two classes are same, the naturally trained model performed better on class plus 1 and class minus 1. This section studied that the performance of the adversarial trained linear model on distribution D star. Without loss of generality, we consider the L infinity norm attack in adversarial training and testing. In the case, the perturbation set can be expressed as here. The radius epsilon of the perturbation set can be used to adjust the level of attack. Obviously, large epsilon means that adversarial can generate stronger adversarial examples which can easily trick the trained model into making incorrect prediction. For simplicity, we denote risk of adversarial training as here. Similarly, the adversarial trained model performed better on class plus 1 than class minus 1, which indicate that the example in class minus 1 are more vulnerable than those in class plus 1. They use variance of class-wise robust accuracy VCRA to quantitatively measure the model fairness. The definition of VCRA is presented in definition 5.4. From theorem 5.7, we can find VCRA of FNet is less than VCRA of F adversarial training. The result of theorems 5.7 suggests that adversarial training easily leads to severe robust fairness issue than natural training. They propose a novel fairly adversarial training FAT to mitigate the trade-off between average robustness and robust fairness. The analytical results in previous section and equation 10 show that we can control the variance of class-wise robust accuracy by controlling the variance of class-wise adversarial risk. The theorem 6.1 provides a theoretical guarantee for using the variance of class-wise adversarial risk to trade off average robustness against robust fairness. Experiments are conducted on the benchmark dataset CIFAR-10 and CIFAR-100. Based on ResNet 18, they compare the proposed FAT with MERDI on two datasets with different perturbation ready. From table 3, we can observe that FAT significantly reduced the variance of class-wise robust accuracy for various perturbation ready. The results from table 3 and 4 further show that with increasing epsilon, the average robust accuracy and the variance of class-wise robust accuracy of FAT increases, which is consistent with theory. Therefore, FAT can alleviate the robust fairness problem and mitigate the trade-off between average robustness and robust fairness. And this is the end of reviewing the paper. Thank you for listening, and from now on, let's move on to the next paper review.
Hello, this is Team 9's presentation on paper User-Level Private Convex Optimization. My name is Moongi Choi, and alongside is my teammate Haechan Kim. Let's begin with a brief overview. This research aims to develop a user-level differential privacy convex optimization algorithm. The goal is to create an algorithm that satisfies user-level DP with access risk dependent on the number of users and items from each user. The algorithm only requires the gradient usage condition on the loss function. Differential privacy aims to protect individual data points within a dataset from being distinguished by an adversary. Here we see representation of how adding noise to the output function helps achieve this privacy under this epsilon delta privacy budget. Adversaries should not be able to detect differences between any two datasets differing in a single user. Convex optimization involves minimizing a convex function over a convex set. People focuses on this empirical risk minimization and stochastic convex optimization problem with gradient usage condition on the loss function. It tries to replace original minimization algorithm with its own differential privacy algorithm and analyzes how it causes extra inefficient access risk caused by the algorithm. The task is to find a user-level differential privacy algorithm with a given privacy budget, solving ERM and SEO problems with extra access risk with vectors mentioned previously. The hypothesis is that the dataset consists of n users, each with m items, and is formed by randomly assigning items to users from an IID distribution. This slide introduces the core algorithms developed in the paper. Author's final goal is to create TP algorithm on ERM and SEO problems. To do this, deletion output perturbation algorithm creates a basic differential privacy wrapper that maps datasets to privacy protected form with extra noise. Under some condition, it turns out to be identity function plus noise. Stochastic output perturbation algorithm uses deletion output perturbation algorithm in convex optimization context. Lastly, our final goal, phased ERM and phased SEO, uses this stochastic output perturbation algorithm as a basic block instead of usual minimization algorithm for convex loss minimization. The most important contribution of this paper is deletion output perturbation algorithm. Deletion output perturbation algorithm is about mapping dataset X to a collection of datasets close to X, yet holds sensitivity bound. The problem is that our current notion of sensitivity is too broad to capture more precise condition on values of single differing user. Thus, at point 1, paper defines a single user deletion difference to be more specific. There are two notations. X minus I just means that we delete i's user from X. X minus ZS means that we delete set of users from X. Single deletion sensitivity is specifically notated as follows. Point 2 is that we need to map varying X to a collection of datasets, such that each member forms from X and each member holds sensitivity boundary condition as follows. This property is called stability, and it just means that all members X minus S satisfies this chain property where single deletion will only give max difference delta. We will encode X as any member of X minus S, but one with closest to X, such that it is formed by minimal deletion, will be the best. Point 3 is that if there is a neighboring X prime with a single user difference, we can form relationship by just doing one more deletion from this X prime. Specifically, from any encodings formed by deletion from X and X prime, encodings X hat and X prime hat meets in one node of the chain at maximum 4k deletion. Thus, we have bounded neighboring dataset sensitivity. And then we can just add suitable nodes to the bound to hide the difference. Note that this neighboring dataset relationship holds in encodings with deletion R1 and R1 plus 1, so we must bound the final relationship between them. This can be done by sampling R1 as TD Laplace distribution, which has epsilon delta probability relationship between neighboring encoding settings. So this is the full algorithm. On conditioning sensitivity parameter, which controls the required Gaussian noise level, we map X to a best member of stable collection by hyperparameter delta. If this encoding fails, algorithm just returns a failure, but if it succeeds, we can just use this encoding, which has bounded sensitivity, and by adding noise of corresponding amplitude, we can achieve this privacy budget epsilon and delta. Note that this algorithm returns our identity function plus noise if this dataset X satisfies some property. And this is the diagram of the algorithm. It shows how datasets are mapped to certain member of the stable collection, and we add noise to ensure that privacy is maintained. Stochastic output perturbation algorithm is just deletion output perturbation algorithm applied in convex optimization problem with IID random permutation of the dataset. It turns out natural deletion sensitivity difference is close to this amplitude with probability at least 1 minus beta, and we just add stable noise level as in the red box. Thus, we have found a basic diffraction privacy algorithm that works as identity function plus noise under this orange block condition that works to minimize convex gradient Lipschitz loss. This stochastic output perturbation algorithm serves as a replacement block for the minimization algorithm. Obviously, this algorithm is differential privacy since every statistical fetch from dataset is processed by our differential privacy algorithm. But the downside is that additional noise causes imperfection as extra average excess loss. Note that we need to scale privacy budget t times since we assess the dataset t times. Phased SEO is just phased ERM with batched users, and just basic algorithm works in the same way as previous slide. Due to the consideration of simple user deletion and deletion output perturbation algorithm, the paper was able to capture all the crucial factor M, which is the number of items provided by each user. Finally, we can see the access risk factors in all previous algorithms and the paper's algorithms. It shows that the paper succeeded in capturing closure factor M in user-level DP-ERM. Other contributions include less conditioning on minimal number of users and convex conditions related to the loss function. However, the author pointed out that there are about 2 inefficiencies caused by their algorithm. The author showed that their algorithm is almost nearly optimal, almost meeting the theoretical lower bound with the dependency on NMN factor being tight, but the dependency in privacy budget epsilon and delta not being tight. Also, there was extra calculation bottleneck during encoding stage of deletion output perturbation algorithm. Thankfully, the runtime is shown to be polynomial with almost high probability, but the worst case is not yet analyzed. Thank you for listening.